Hi everyone, I'm Hana Jug, and today I'm going to talk about AAV and Lentiviral purification when using CIM products. So I'm a product manager for the field of envelope viruses, VLPs, and EVs at Sartorius via separations. So maybe you will ask, okay, why she's talking about AAV. So my aim is to really give you some overview to basically find a solution in our technology. And of course, then later I can provide you with some more educated contacts regarding the AAV. But regarding the lentivirus field, you can easily contact me. So who we are Sartorius via separations. We are based in Slovenia. We are monolith experts, so the leading developer of monolithic technology called convective interaction media, so CIM. We have more than 25 years of experience and over 250 employees. We are also equipped with BSL-1 and BSL-2 laboratories. So we are a leading expert in the purification of large biomolecules such as AAV, adenovirus, lentivirus, influenza, also pDNA, mRNA, as well as LMPs, exosomes, and many more. A few years ago, we were acquired by Sartorius and also named as a center of excellence in gene therapy. So we can provide you with solutions for downstream process development, for manufacturing, as well as analytical method development. This is our really comprehensive monolithic chromatography portfolio. So basically, we offer preparative chromatography, where we usually start, or let's say suggest clients to start with screening chromatography. So they use high throughput screening solution, where it's worth to mention our CIM monolithic well plates, our CIM discs, and our CIM octa products. So the plates are 96 well or 24 well plates for really high throughput purification. You can screen many different conditions with them. Then CIMIC disc, they came in a pack of 3 discs of 0.1 milliliter disc, and you can easily pack them into the housing and again test different conditions. The third option is 18-line column, so columns with 50 microliter monolith inside and really easy handling. Then if we go a bit higher on the scale, we have our preparative columns, so the CIM Multus line, and they are in range from 1 milliliter to 40 liter. They are compatible with basically all standard chromatography system. They came in wide range of ligands. They're ready to use, so no pre-packing is needed. They come also in CGMP compliant mode, and they are caustic stable. On the other hand, we also offer analytical solutions. So not only analytical columns called the CIMAC line, where the monolith is packed into stainless steel. It offers high resolution and really short analysis time, but also PATfix liquid chromatography biosystems. They are especially good for process control and also product release quality control. They can be also preloaded and pre-validated with the methods, and you can buy them also with reference standards which are available. Then, as a third part of our portfolio, we offer also Cornerstone Biomanufacturing Development Service. So what's this? This is basically the single method or start-to-finish procedure, which includes also SOPs, includes trainings, tech transfer, also scale-up experiments, and on-site support. Basically, we can develop the purification method for the client for any biomolecule like pDNA, mRNA, for envelope viruses, non-envelope viruses, for LNPs, bacteriophages, as well as we are entering also in human plasma proteins. The focus here is always that the purification process is based on our products So in preparative part, this would be CIM Monoliths monoliths. Then we offer also analytical development service. So those are single methods or full process monitoring to really see the product quantity and quality, to monitor impurity type and quantity, and also to monitor basically the whole process from start to finish. So there are method development, there are validation strategies behind, and basically verification for viruses, exosomes, pDNA, again mRNA, also for impurities and other biomolecules. Here the focus is not only on the CIMAC analytical columns, but also on PATfix system, so really to provide you a broader insight into the sample composition with all the detectors that come with PATfix. So our labs are equipped with many other analytical methods, and we are using them especially as an orthogonal analytical methods to support our analytical development. Then we offer also trainings. So those are really on-site technical trainings and process demonstrations. Here we are really flexible. The trainings are from 1 to 5 days, and we really let you work with our columns in our labs. So process demonstrations and technical trainings are specifically for purification and analytical scientists. Those trainings are designed in a way that we meet clients' wishes and needs, and a client can also bring their own sample for testing. Then, as a fourth part, we offer also custom monolith development and manufacture in sense of immobilization protocols for basically any ligand, whether this is affinity, ion exchange, Hick, and many more. So we can prepare custom monoliths at basically any scale, or we can provide you with a protocol if you like to do the immobilization on your own. This is the list of our products in terms of size. So all the chemistries available are also available in the format from 1 milliliter to 40 liter column. Of course, usually the process development starts with smaller units, sometimes with high throughput solutions, sometimes with 1 milliliter column, which is then linearly scalable up to 40 liter. So basically what you need to consider here is that if you apply 5 CV per minute flow rate on 1 milliliter scale, you can go easily with 5 CV per minute, for example, on 40 milliliter scale. Here is the list of all the surface chemistry we offer. So anion exchangers, cation exchangers, hydrophobic, hydrophilic chemistries, those are more, let's say, important for today's talk since we use them a lot in the virus purification field. But of course, we offer also affinity, mixed mode, and activated monoliths. So with an exception of Prima S, the right part of this slide is more for the nucleic acid purification and for plasma protein purification. So we will be today more focusing on this part here. Just 2 slides about our technology. So what are the monoliths? The monoliths are the tubes. They look like a piece of chalk, and they are packed into the housing. So here is the electron microscopy picture, and the gray part is the matrix, and the black part are the channels in the chromatography media. So in the channels, on the surface of the channels, there are binding sites for our biomolecules. And the key advantages of the monoliths are high binding capacity for large biomolecules, because there is radial geometry, which enables really higher volumetric throughput by increasing the intake surface area and also decreasing the bed height. So the entire channel surface area is basically available for binding, and this results in higher capacity. We don't have dead-end pores, which means that there is no entrapment of the solutes, and that there is no carryover if we are doing multiple runs on the monolith. We offer different channel size, so standardized size are 1.3, 2, and 6 micron channels in diameter. So those big channels really allow for easy passage of large biomolecules. And also, what is very important here, there is no shear stress. So for the viruses, especially enveloped viruses, which are very sensitive, this means that you can still obtain very high recoveries. The mass transport with monoliths is convective, which results in flow-independent capacity and resolution. And on this slide, I would like to explain a bit more about the resolution and dynamic binding capacity. So on the left part, we can see the protein separation on the monolith if we apply different flow rates. So basically, the resolution remains the same even though we have higher flow rates, and basically the chromatograms overlap. So if we do the same with resin, where the matrix is diffusive, so if we apply higher flow rates, we will lose the resolution. And regarding the dynamic binding capacity, similar experiments were done. So for the monolith, we applied different flow rates and basically perform breakthrough curves. And as you can see, the breakthrough curves overlap. If we do the same thing with the diffusive matrix, we will lose the dynamic binding capacity when we apply higher flow rate. So as a sum up of this slide, you can work really fast with monoliths. You can apply really high flow rates, and you will not lose the resolution or dynamic binding capacity. So now let's dig into AAV purification. For those who were attending the Daniel's lecture yesterday about AAV purification and cost reduction, you maybe saw the application of capture and polishing steps, so the application of CIM Monoliths SO3 and QA-HR monoliths in those two steps. But basically, those two steps are, let's say, some standard procedures when we are purifying AAV, but sometimes our purification method might start with one step before, so a pre-capture step where we are using CIM Monoliths OH column, and I will start with explanation of this step first. So we recommend using this type of column especially for the extracellular AAVs, where the lysis is not needed, but of course it can be applied with slight changes in the protocol also for other types of materials. So there is a preferential exclusion chromatography with a really uncharged neutral hydrophilic ligand. It retains large species in the presence of cosmotropic salts. It does elute with decreasing salt, so species will elute in order of increasing size. And it can serve us as a great alternative to TFF. So it's faster, and basically the result is comparable to TFF. It does remove media components and also major host cell impurities, so majority of the proteins are found in the flow-through. This is also why the signal is so high. It can concentrate and purify AAV in one step, let's say here in step elution. So the purification is really fast. It's also gentle because there are weak interactions between particles and solution. So the particles in solution and the surface on the column. And of course, there is no shear stress. The next step, so we proceed from pre-capture to capture step. For the capture step, we are using CIM Monoliths SO3 column. This is the strong cation exchanger. It can serve as an alternative to affinity capture step, and the benefit of it is that it can bind any serotype, so it's not serotype dependent. The capacities that can be reached with this column are in a range of e to the power of 12 to the e to the power of 14 viral genome per milliliter. So this really depends on the sample preparation, so the steps before capture. Here we can really achieve high recovery of potent capsids, so elution at higher pH, around 3.5 or higher. And we really expect the recovery of 90% or even higher. So most of the impurities are removed here, so this means better performance of the polishing step. The column is, of course, reusable. You can easily clean it with sodium hydroxide solution. It has high resolution, and it is really, in terms of yields and in terms of purification, similar to affinity column. So let's now dig to the most important part for the AAV full capsid enrichment, so the polishing step. We have, let's say, 3 options how to enrich your full AAV fraction. And those 3 options are based on different, let's say, different monoliths, different chemistries. Each of the chemistry can separate according to slightly different principle. So let's look first on the CIM Monoliths QAHR column. So this is the quaternary amine ligand. It's very strong anion exchanger. It does retain positively charged at any pH, basically, and most probably you all know it as an industry standard for empty-full separation. So here the separation really occurs based on slight charge differences between empties and fulls. It binds any serotype. The sample is loaded at low conductivity, around 2 to 5 millisiemens, and elution is then performed with ascending salt gradient. The column is effective in the range of pHs from 8.5 to 9.5. The capacity are really high here, so more than 2 to the power of 14 viral genome per milliliter of the column. And also that column is reusable, so you can clean it with sodium hydroxide. Here we are showing the full AAV separation, so it is AAV28 coming from SO3 column, and basically you can see the 85% of full capsid with 80 to 95% recovery. The second option is CIM Monoliths Prima S. This is slightly different column. So it works as a multimodal column. So it has unique combination of weak anion exchanger and also hydrogen bonding that achieves different selectivity compared to the QA ligand. Best separation is achieved when we use ascending pH gradient, let's say from 7 to 10, at low conductivity. So the characteristics for, let's say, perfect run would be that we are loading the sample at low conductivity, 2.5 millisiemens per centimeter or lower. We can add magnesium chloride during loading and elution. The effective pH working range is from 7 to 10, and also this column is reusable. You can clean it with 0.1 molar sodium hydroxide. You can see also that separation of anti-full here is slightly different, really, because there's a different selectivity compared to the previous ligand. And, oops. And if we move on the third option is the most complex one, so it's called PRIMA-T. So PRIMA-T functions as a multimodal ligand, again, weak anion exchanger, hydrogen bonding properties, and additionally also metal affinity coordination effect. So here the capacities are again very high, 2 to the power of 14 viral genome per milliliter. It can bind AAV2, AAV8, and AAV9. So those are the 3 samples that were tested so far. The sample needs to be loaded at low conductivity. Again, we are adding magnesium chloride in elution, which enables full AAV subspecies separation, as you can see here. So one population of fulls here and the other in the shoulder. So sodium chloride elution elutes major of empties AAV, which are more strongly bind at fulls. The effective range is from 7 to 9.5 pH, and also that column is reusable, so you can easily clean it with 1 molar sodium hydroxide. So, of course, when you have such complex methods for full enrichment, you need to take into account a lot of critical parameters that we need to keep in mind, like column equilibration, like buffer preparation, like sample amount, surrounding temperature, and many others. So here, really, what I would like to point out is that basically we always offer help. We always offer suggestions to the clients which way to go, and as well as you can basically find the best solution also through feasibility studies and process development, like corner store process development service. And now let's jump to lentivirus purification. This will be more like a case study, how we approach the lentivirus purification using monoliths, and how we start a study with an aim to really improve the yield and to basically end with a product with really high infectivity. So in this study, we were particularly focused on chromatographic steps, so the purification step, and all the other steps were not in our focus, let's say. But of course, we know that there are many steps for the successful lentivirus separation, and every step needs to work hand in hand with all the other steps. So having this in mind, we firstly screen the columns. So from the literature, from the experiences, we were focused on anion exchanger first. And basically, we compare different monoliths in this case. So strong anion exchanger and weak anion exchanger, so CIM Multus QA and CIM Multus DEAE. In both cases, we start immediately with 6-micron channels diameter, because we know that lentivirus is very sensitive biomolecule, and basically with larger channel size, we can really have very fast purification procedure. So we applied the lentivirus sample on both columns with more or less similar conditions. And as you can see, the chromatograms looks very different. So here we applied also mass detector, which is the black line here and is really one additional orthogonal detector showing us or indicating us the presence of particles, in our case, the lentivirus. to really see the difference between these two columns, we were primarily focused on infectivity recovery. So the infectious recovery was the most important part, and then also the rest, so removal of impurities as well as other characteristics. So in this case, we noticed that basically QA compared to DEAE performed better. It does show better potential for further development, especially because the infective recovery was higher. So regarding the protein removal, both chemistries, both columns were more or less the same, so around 90 to 96% protein removal. So we approach this case firstly with some really basic study to see which conditions needed to be optimized during the study further. And we select the buffer, the salt, and also the sugar to see whether one of them or maybe all of them have any effect on the lentivirus recovery. So we screen different buffers and see that basically, with an exception of hippies, all the other tested buffers were basically fine. So we decided to continue our study with BTP just because of practical reasons. Then the same, some different salts were tested. And with an exception of 2 salts, all the rest tested salts were more or less the same. So the salt was used especially for the elution in this study. And according to well-known sodium chloride, which is also quite cheap, we decided to continue our study with sodium chloride. And then we also screen for the sugar addition into the buffers. But here, really, you can see that basically all the tested sugars performed more or less similar. So we decided to move further with saccharose, again, very known component, and you will see later what we notice. So from this study, we also saw that loading sample conditions were really important and that we need to modify them to achieve better recoveries. And sodium chloride and saccharose were selected really for further optimization. So we did a series of DOE studies to really focus on all mentioned parameters. And in first DOE study, we were focusing on salt concentration, saccharose concentration, and also pH. So when I'm saying salt concentration, we especially want to evaluate what happens if we add some salt already in the loading condition, so already in the loading buffer. And we noticed that basically sodium chloride has the strongest effect in the first DOE study. We also noticed that basically saccharose has no effect on the recovery. So this was quite a surprise for us because we were assuming that saccharose will somehow have a positive effect on virus stability. So we decided to repeat some conditions in DOE study number 2. We checked for additional salt concentrations, even higher. We checked for also even higher concentrations of saccharose. And from study 1, we noticed that slightly lower pH than expected works better. So in study 2, we choose to test also lower pHs. And what we found out was that increased sodium chloride concentration and pH reduction improve recovery, and again, that saccharose has no effect on recovery. Therefore, for the further studies, we exclude saccharose from the buffers, and we focus on additions to the buffers, so magnesium chloride and poloxamer, and histidine and arginine. So here we notice that magnesium chloride has addition. So a magnesium chloride addition has positive effect on recovery. And when choosing between histidine and arginine, we also see that arginine performed better. So with all these tested parameters, we basically come to a conclusion what the perfect parameters can be. And we did the scale up from 96 well plate, where all those DOE studies were carried on, to 1 milliliter column. And if you remember the chromatogram from the first Lenti slide, the QA column performed in a way that there were multiple peaks. And you can see that with improved conditions, basically there is only one peak in elution with really high moles, indicating the presence of particles in this fraction. We also have enough material here to really do some extensive analytics. So we checked all the fractions from this run, also with different analytical methods. We checked for infectivity, and basically the infective recovery was 70%. We did also PCR and Videotrop analytics, and with these two analytics, the recovery was lower, 40 and 46%. We also checked for the capacity. So the capacity was calculated to be around 3 to the power of 12 particles per milliliter. So why there is a difference between infective recovery and particle recovery? You can see the indication, or let's say explanation here. So we additionally did another analytics, so leprechaun analytics, where you basically monitor the presence of 3 very important components of the lentivirus, the presence of VSVG, P24 capsid protein, and the presence of RNA. And if all 3 components are present, you can see such particles colored in yellow on this graph. And if any of these 3 components is missing, then basically the particle is whether black, blue, or gray. So what we can conclude out of this graph is that with this purification method, we basically enrich the particles that contain all 3 components. So you can see that from clarified harvest to elution, the particle enrichment was really obvious. So this is also an indication, or maybe explanation, why there is a difference in the recovery assessment with infectivity test or with particle tests. So to summarize, QA monoliths are really suitable tool for lentivirus purification. We used 96 well plates and DOE approach, and we successfully optimized lentivirus chromatography process from 20 to 70% recovery. And during the purification process, we also successfully enriched the full lentivirus particles, or let's say positive particles for these 3 components, while also removing other particle impurities. This is my last slide, but before ending, I would just like to invite you to stop by our 3 posters. So poster number 1 is talking about LNP purification approach, very hot topic now. And then we have 2 posters on AAV purification. The first one is about the differences, or let's say comparison of capture simultus SO3 and affinity method. It's number 73. And the third poster, number 49, is about the polishing step. You can stop by and we can give you some more knowledge about that. Thank you for your attention.
Thank you, Hana. Very informative presentation. I'm sure there are some questions. No? Perhaps I can start with one. For the lentivirus, you've shown this particle composition to increase from harvest to elution in the end. But in two other fractions, the flow-through and something, this composition was actually lower. So can you explain what's happening here?
So, of course, you can see that basically, most probably, we are losing some, let's say, positive particles in those fractions too. But you need to somehow compromise and achieve higher yield on one point and also removal of all the impurities on the other point. So basically, I would say that this is what we need to risk in order to achieve really pure lentivirus in the end.
Thank you. Any other question came to mind? Yeah?
So I saw that you are using the Thank you. So I saw that you are using the 96 well plate for the screening and DOE, right? Have you done some fundamental study to compare well to well or plate to plate consistency of this format?
Yes, we did, and we also tested the same samples on different points of the plate, and basically it performs very well. Yeah.
Sounds great. Thank you.
Very nice talk. So the infectious particle recovery that you're showing us, is that a step recovery, or is that 20 to 70% that you achieved an overall recovery of lenti?
It's a step recovery because we were focusing only on the chromatography step, yeah. So
okay.
The recovery of the chromatography step.
That's great, yeah. The second question would be, I'm blanking out now. I'll ask again. Thank you.
At the chromatography step of lentiviral vector, the pH itself is extremely low, I guess. And also, I'm curious, how did you prepare the feeding sample? Because the pH and a salt adjustment for feeding sample is required, so I'm asking about that.
Yeah, so maybe we can jump on this picture here. So the pH where we were working was 6.75, and yes, the concentration of salt in loading was really high, but we checked the lentivirus infectivity with the presence of such a high salt, and basically we didn't see any negative effect. So yeah, we loaded the lentivirus with 0.5 molar sodium chloride, and then in this case, eluted in linear gradient, ending with 2 molar sodium chloride. Right immediately when the lentivirus is eluted from the column, we dilute it to reduce the salt concentration, and we noticed that basically the ideal conductivity, the final conductivity, was around 20 millisiemens. So this was the conductivity we wanted to reach when diluting the final fraction, and in such condition, then we froze the material.
Okay. And for feeding sample, is dilution of a harvest or something?
In the beginning, yes. So we dilute the harvest, and to really meet the binding conditions.
Thank you.
Hi, thanks for this talk. With the AAV polishing, I think you showed a chromatogram where there was empty, full, and then damaged coming out after. Could you speak a little bit more about the identity of those damaged, or how you came up with that title?
Yes, maybe I will ask my colleague to better explain. Here, you mean? Yeah.
Yeah, I can take over instead of Hana. Maya Liska is from Sartorius BIA. Working on the QA column, we many times see this third peak. I'm not sure if you've seen that as well. And it's more electronegative. This is definitely. We don't know yet what is really causing this, but in some cases, with different capturing strategies, this peak is higher or lower. There were some talks, I believe, on ASGCT showing that this is connected with the deamidation. So it might be the pH, temperature before in the process affecting the size of this peak. And we definitely want to separate this out so we don't capture it in a, together with the full elution.
Staying with this story, so have you characterized that third peak? So do we know that's not something else, like partials or something else? How do we know?
We tested for many different analytics, and I don't think we have already a story what it is. So usually we try the ultracentrifuge, and it seems like it's of the same density as the full. Mass photometry also shows, partially empties, partial fulls, so it's not yet clear, I believe, but maybe the deamidation hypothesis is the most probable one.
Okay, thank you.
Thanks.